last time we talked about cement, and hopefully we are going to almost finish talking about it today. And pay attention that you need to read chapter 6 of the textbook in parallel. There is no way we can look at all the details in the class. So you saw the video on cement hydration, and you kind of see that you start from having the cement particles in water, and then around the particles, if you remember in the video, you have hydration products, and then they increase in volume until you have them bridging between the particles, and that's when you start to have transition from plastic to solid state, and ultimately hardening and strength of concrete, so load-bearing properties. So this is kind of summarizing what I just said. You start in the first couple of hours going from plastic to solid, and then you have final set when the material is hard enough then to sustain load. And it can be more or less. There are several factors, as we will see in a second. And some of these factors we talked about last time. The fineness of cement particles. If it is finer, what happens? What do you think happens? Yes. Exactly, it sets faster. And the reason is that you have more surface area in contact with water, and you are going to have faster setting. And it also depends on composition. Last time I showed you that cement has different components, and then each one of them has a different strength gain properties. And also temperature. Normally increasing temperature will accelerate setting. So this is what we learned last time, and you have seen videos which I think are nicer than what you see here. So please make sure that you see all those videos, let's say before Monday, where you will have a quiz on cement. Because those information are a part of the instructions. And we don't need to go through the details of these are the videos. So what's important is that the main product of cement hydration is calcium silicate hydrate. This is sometimes it's called cash gel, and you should look at the microscopic views of this material. You see that it is not crystalline, it's amorphous. It's kind of crazy looking, as you can see. This is what carries the strength because it's stable, it doesn't dissolve in water. What else? The surface area is very high, 400 square meter per gram. That's really, really high. So you have a lot of surface area to react. You have another product of cement hydration, and this is calcium hydroxide. This is CH. Sometimes you call it Portlandite. And this one is crystalline, as you can see here in the picture. You see clearly a crystal. And this one dissolves in water, so it doesn't really help much to the strength of cement. We talked about heat generation last time, that cement hydration is an exothermic process, meaning that it generates heat, and you saw that in the lab you can measure this heat generation, and I hope you all remember this curve in the video. So we have different phases of heat generation during cement hydration. Previous one? This information related to that are in the videos, so that's why I'm going very fast. I'm assuming that you all came having reviewed those videos. What is important is really to know that you have heat generating during semen hydration, and also that this heat is a proxy for knowing how progressed is the hydration process. So from this heat generation, we can actually find out where we are in the process of semen hydration. And this is super important. You need to know the shape of this curve by heart. You need to understand what's happening. So in the very beginning, you have a large heat release. But what is more important is the second phase, where it's a dormant period, where nothing is happening. So it means that it's kind of the setting stops. And this is because you have the hydration products around the particles, and that prevents further reaction from happening. And this is interesting because it gives us the time, for example, to transport the material to the job site. Afterwards, you are going to have the setting, initial setting. It's very accelerated, as you can see. You have a lot of heat release, and then the material reaches the final set, which means that it actually can start carrying load. This is super important for engineers because that's when you know how long you have to wait to open a highway. Or yes, please.
What happens when it's in like a cement mixer? Like, does that extend the time longer because it's constantly being rotated?
Right. So this is that is basically in this period when you are carrying it to the job site.
Right.
Yeah.
But that doesn't extend the time at all. Like, it's still, you only have that hour.
Yeah, it's more than an hour, and there are some admixtures you can add to increase that time. Let's say if your job site is very far away. Yeah. But if you miscalculate that, you know what happens, right? Then you cannot get anything out of the mixer. And afterwards, you have the acceleration period, and finally a steady state. What is important is basically looking to see how these stages, they translate to the different phases of construction. So this is batching. This, you normally try to do that in the initial phase. And then when you want to transport is when you actually have, you start to have this dormant period. And this is nominal, it doesn't have to be exactly that. As you will see, this depends really on the type of semen, on the weather even. If it is hotter, everything happens faster. If you have admixtures, etc. So then you basically use the time before the setting really starts for placement, because you also need the material to be workable. You don't want it to be set when you want to place it. Make this bigger. I don't know if you see the pictures well. You see them? You see what's going on? And then when the initial set starts, you start basically finishing. That means you make the surface smooth, and then you do the curing, which means that you spray the material with water typically, as you may recognize in this picture. I'm not sure how clear it is, but you have to let the material cure in a moisture state to gain enough strength. You may have seen people having water, they splash water on newly placed concrete slabs. So this is to let it cure. We'll talk about this more later. And then once everything is done and you are in the deacceleration phase, then you can do things like cutting, etc. it's super important that you remember the shape of this curve and you remember how this is related to the construction stages when you are constructing any kind of concrete. Any questions? Everyone has the curve. Make sure that things align correctly and you know why things are happening. And this curve it looks like this when there is some exchange with the surrounding. If you didn't have any exchange, if you had adiabatic kind of situation, the temperature would just rise and the material would reach the temperatures of boiling water. So that's also something to keep in mind. So last time we talked about composition. It turns out that we have different types of cement. So typically for normal job you use ordinary Portland cement, you use number 1 or 2, but it's becoming more common to use high early strengths or in a special situation, for example, if you have a massive structure like a dam, if you are pouring concrete for something like a dam, then you want to have low heat of hydration, otherwise there will be a lot of heat generated. Or if the weather is very warm, where you have your project. So we want to take a look a little bit at the composition of each of these cements. So to see better based on our understanding of the composition, we can explain these properties. Does anyone have a piece of paper? Everyone is done writing? If you're not done writing, just stop me, ask me to go back. So here is kind of thank you. So you see that these are also different types. You normally use leathering, like Roman leathers, and I have marked the important things here, but it's worthwhile to read this table, which is from the book, as you see from chapter 6, and you see that, for example, high early strengths, you want to use it for cold weather, or low heat of hydration when you have hot weather or when the mass of a structure is very high. And types 1 and 2 is something that we normally use. What is more important is this. So on the top you see the different types. So this is the type. And here you are looking at the composition. If you remember, different components, they have different properties. And there is also fineness, which we talked about last time. So let's analyze this a little bit. For example, let's compare type 1 and type 3. What is different between the two in terms of composition? You can look at it, right? Type 3 and type 1. What is different? You have more C3S and the fineness is larger. So let's look back at something that we discussed last time about how different components of cement gain strength. So you need to have this graph, which now disappeared. Oh no. In your mind when we are discussing different types of cement. So we see that C3S, you have high initial strength gain, right? But afterwards it slows down. C3A is also the same, but afterwards it kind of stays the same, reaches a plateau. And C2S, in the beginning it doesn't do much, but then it contributes to later strength. So if you have a lot of strength gain, think about hydration. That means that hydration is very fast in the beginning, right? So this is something you need to know. So I'm not going to give you these graphs, but I may ask you to compare different types of cement, just knowing the composition, to compare them in terms of heat generation and in terms of strength. So here, what we are looking at, C3S is more for type 3 than type 1. So what does it say? You need to be able to make this connection. That means that you have much more early strength development because you have more C3S. Does it make sense? And then fineness is much larger. That is another factor. That means that the cement can react much faster in the beginning. So you are going to have a lot more heat generation, and in the beginning the strength is going to develop very fast compared to type 1. And then type 4 is low heat. So look at the composition. Now this time, tell me what makes it a low heat cement. Why type 4 is low heat generation? I said that this is something we want to use, for example, if you have a dam, a massive structure, if the weather is very, very hot where your project is, you're working in Arizona or somewhere like that. Why do you think that type 3, just 4, just looking at the composition, why do you think that the heat is so much lower than the previous ones?
C2S is high.
Exactly, C2S is high, so in the beginning it doesn't react much. What else? Fineness. Exactly, fineness is also lower. So that's kind of how you have to look at different types. And if you look at the earlier strengths, you can see that type 3 develops very fast and type 4 is the slowest in terms of how fast it develops to a certain level of strength. So again, I cannot emphasize how important this is to understand cement hydration and this relationship between composition and why we see this different behavior between different types of cement. Questions? You guys look tired this morning, like a little bit sleepy maybe? What happened? There was a party last night I wasn't invited to. It's fine. It's like the end of the semester, everyone is like, okay, a few more weeks. Okay. Another very important discussion related to cement is the frosting. Now, it's not difficult, but I want you to pay attention and then for once and all you know what this is about. It turns out that, is this the basket? Yes. So I'm passing an attendance sheet. Please write down your name, initial, and put a number also if there is. There are different types of words inside cement. And it turns out that they do different things in terms of properties. And it's super important to understand their differences. Because they affect everything. They affect the strength of concrete, they affect its durability, which means weather resistance, so weathering, and stability, for example, shrinkage. The very, very small, tiny voids are between the CSH, like cache layers. They are very tiny, nanometer scale. Typically, you can't get rid of the water in these voids unless the relative humidity comes very, very low. And if this happens, the material shrinks a lot. So that's why they are very, very important. If the humidity is very low, they cause a lot of shrinkage. So it's important. The very important ones are capillary voids. These are kind of water-filled spaces, so when you add water in the mixture, when the water evaporates, this is what is staying there. Look at the dimensions. You won't be able to see them. A hairline is 50 micrometer, and the largest of those is 10 micrometers, so probably you won't be able to see it. They are very important because they are kind of the channels which lead water inside the material. And they decrease with time. They are influenced by water to cement ratio. You are going to see that very soon. And they cause less shrinkage, but the smaller part of them can cause quite a bit of shrinkage. And shrinkage is the decrease in volume of concrete, which causes a lot of cracking. So, everyone, you are writing something down. So these are capillary pores. And then there are larger pores which you may have seen. If you have ever been curious and looked carefully at concrete, you may have seen some pores. These are something which happens during placing. They can be very, very large, and they can be even up to millimeter size, but they can be also smaller. A little bit of it is expected, but if you have a lot, your strength is going to go down and permeability is going to increase. Why are we so concerned about permeability? A strength going down, okay, we all know it's not a good thing. But why do we care about increasing permeability?
If water gets in, then it freezes all sides.
For example, water, when it gets into concrete, it brings with it all sorts of things. It can cause freeze and thaw if you have a weather like we have here. It also can bring salt in, remember corrosion? So we don't like to have too much permeability. It reduces the durability of material. So increasing permeability, it reduces durability of the material. So you see that your driveway, you need to replace it every couple of years because you see scaling, pieces of the material is chunked off, and yeah. So that's why. And there is another problem which also increases the amount of air voids, and this is honeycombing. During the placement, you need to vibrate or mix concrete. If you do this a lot, then it causes segregation. That means that kind of the aggregates and cement, they go their own separate ways. So you'll have some pieces of aggregates here with not enough cement in between them, and you see something like that, and it's very porous. You don't have you don't have cement between aggregates, and that's not something good, and that's not something you want to have. So these are kind of the air voids which are naturally operating in concrete. As engineers, you induce air entraining. You induce some air entrained bubbles inside the material. So to reduce the damage due to freeze-thaw, what you do is during the mix, you add an admixture, which is called air entraining agent. It's really like fish liquid. It creates bubbles inside the material, and then when it hardens, these are less than 100 micrometers. Think about the hair size. They're very tiny, and distribute them. So when the material is going through freeze-thaw cycles, the water escapes to these air-entrained voids, and it doesn't, when it increases in volume during the freezing cycle, then it has a place to go. It doesn't push concrete as much, so you don't get too much cracking. Okay, so this is something we want to have. What is important is not that you have a lot of it, it's more important that you have it distributed. You don't want them to be large and concentrated. You want them to be tiny, but to be everywhere inside your mixture, so that this water can escape and you don't have problems that you have if you don't do it. It is now like common practice. Almost every mixture has this air entraining agent. It's not something of an exotic admixture anymore, because people have realized how important it is. It's important here, very important, to realize that when we talk about porosity, we are pretty much looking at capillary voids. We are not looking at large entrapped voids, because these capillary voids, they are the ones which have the most effect on concrete properties. So because they are really like flaws, they are very, very tiny, and they cause a stress concentration, so a strength goes down, and as we just talked about, they also work as conduits to bring water into the material, and that also causes all sorts of things, like you have freeze-thaw problems, and they also bring salt in, which causes corrosion of a steel reinforcement. So when you talk about porosity, remember that large air voids are not included. And just to give you a sense, if you have more porosity, look how permeability, the red curve is increasing, and how the strength is decreasing. This is something you need to know by heart. I mean, you need to know that when porosity is increasing, you lose the strength, and permeability, especially after a certain level, is increasing a lot. This is another curve showing the same thing. This is real experimental data. When you look at the porosity, so this is the ratio of capillary pores to the total volume, and you see that if you have more here is in this direction, the strength is dropping dramatically. And why? We talked about it. You can have shrinkage when the water is evaporating from capillary pores, and then when you have a lot of shrinkage, you are going to have a lot of cracking. This is a common problem. So if the water freezes, we talked about it, they also bring aggressive agents. That's a fancy name to say that they let in salt. Chloride is in salt, and this creates, for example, corrosion. Yeah, so under the microscope, when you look at concrete, you can see these capillary pores as you see in the picture, in the cartoon. They are not that big or they are not round as you see here. They are typically very, very tiny. You see the scale. The whole SEM image is 80 micrometer. Any questions about this? Super important. Just remember that this is not air voids. We are really talking about capillary porosity. So generally, when you have any kind of voids, strength decreases, permeability increases, except for the entrained ones, which we like them to be, and they increase durability. Now, how do we measure porosity? Porosity has a lot to do with the parameter, which is very useful in concrete design, and it's called water cement ratio. If you are doing C57, you have So, water cement ratio is, as the name suggests, the ratio between cement and water. Now, let's say we want to know if we mix, and this ratio is weight-wise. That means weight of water over weight of cement. That's something to remember. So if you mix 100 pounds of cement with 50 pounds of water, you are going to get a water-cement ratio of 0.5. Now the question is, how much porosity you will have. And porosity, as I told you before, is a volume factor. So we need to then do a little bit of calculations to relate one to the other. And that's what we want to do next. It turns out that when you mix one volume, one volume of cement with one volume of water, of course you get 2 volumes of hydrated solid gel. Have this in mind, this is useful. So that means that if you have 1 cubic feet of cement and 1 cubic feet of water, you get 2 cubic feet of cement paste. Gel means here cement paste. It's a glue, really, if you have ever worked with this before. Now, to give you a sense of for different water-cement ratio, what you get in terms of porosity, this graph is showing you that. So look, you have water-cement ratio changing from 0.32 to 0.7, and the porosity is changing from 0%. So the porosity is the volume of voids which are not filled with water, to 37%. So what we can say for sure is that if we have less water to cement ratio, we have less porosity. But we need to be able to calculate. Let's see how it would be calculated. Going back to our water to cement ratio of 0.5. Okay, we have 100 pounds of cement mixed with 50 pounds of water. How do we get the porosity? Well, let's calculate. We know that the reaction or the porosity is based on volume. So let's calculate what does it mean. If we have 100 pounds of cement, how much volume of cement this is? Where did I get 3.15 from? Yes? Exactly. It's a specific gravity of cement. A few lectures ago, I gave you this number. So it's a specific gravity of cement. If it's not given, you can always assume that it's 3.50. It's pretty hard. So this is the volume of cement. How about water? And 62.4 we all know what that is. Yeah? It's just the density of water in the right unit. Now, we know that 1 volume of cement will react with 1 volume of water. So if I have 0.51 cubic feet of cement and 0.8 cubic of water, how much of the water would react with cement? Does it all react? No. How much of it? Ratio 1 to 1. How much? .51, right? 0.51. So if the ratio is 1 to 1, if you only have 0.51 cubic feet of cement, only 0.51 cubic of water can react with it. That's cement and water will react 1 to 1 ratio in volume wise. And they give 1.02 cubic feet of cement paste gel. So how much water will be left? Well, 0.8 minus 0.51. So that would be the pores in the cement paste. And if you divide the volume of pores to the total volume, you get positive. This is total volume. You can write it like that, or you can write it like this. It's the same thing. So it's very simple. Just think about it. All you need to realize is, all you need to know is what water to cement ratio is. It's a weight ratio. Just remember it, write it somewhere. I don't know. It's a weight ratio. And to remember that the reaction is 1 to 1 ratio in volume. If you know that, then it's very simple. Or you also need to know that the porosity is the volume function. But this is something you have seen in other classes. Porosity, you always look at the volume of voids to the total volume. So it's kind of, hopefully it's not something new. So let me let you do one on your own to make sure that you know how to do it. Now, what if the water to cement ratio was 0.4? You can. One thing that I have to mention here is that this 100 pounds of cement and 50 pounds of water is arbitrary. You could have assumed 1,000 and 500. So if you know the water to cement ratio, just assume something so you can work with the numbers. I could have assumed, I don't know, 54 pounds of cement, 27 pounds of water. Anything which has this ratio. And of course, the higher water to cement ratio, the higher porosity, because you have more extra water. Strength goes down, durability also goes down if you have higher porosity. Okay, now work with your neighbors. I've seen quite a lot of check and ask questions. Remember that these 140 are not, they're arbitrary. So if I give you just water to cement ratio, you can just use it. You can just decide if you want to work with 1,000, if you want to work with kilogram, which I doubt you guys would. But if you want to, it's kind of, you just know, if you know the water to cement ratio, you can just assume that you have 1,000 cement, and then you know what is the amount of water. Is this clear what I'm saying? You don't need to have those 100 pounds given. If the ratio is okay, that's what matters. Any questions about that? Why doesn't it's not writing? Interesting. Yes. So if you have, for whatever reason, my stylus is stopped writing, maybe the battery is off. The strength will be lower, will be higher, because when you have lower water to cement ratio, then you have lower porosity. So the durability will be higher, strength will be higher. It's the opposite of the previous, but they were both lower. Don't know what happened with the stylus. So, and here, if you have more water, always you can expect that the strength is lower, shrinkage and creep is higher, permeability is higher, abrasion resistance is lower. Remember abrasion when you have, it's the resistance to damage because of the load when you use that blue drum I showed you, and freeze-thaw resistance is lower. So if you want to compare, here we have A is air entrained and B is not air entrainment, if you want to compare, the air entrainment does reduce the strength a little bit. If you add voids to the material, you're going to lose a little bit of the strength. If you compare A and B, this is from your textbook also, you see the figure on it. But also you can see that for both cases, when you have increasing water to cement ratio, strength is going down, as you can see. And those days are the days that you wait until the material cures. So of course, as you wait longer, the strength is going to be higher and higher. But again, with water to cement ratio, it's decreasing, as you can see. One small quick question. Oh, battery is not a problem. So A is your B. Let's discuss one by one. Let's say why A is wrong. Why the A is wrong? A is wrong for one. Exactly, this is not really, porosity is not really looking at air voids per se, it's the capillary pores. So that's kind of the catch. For porosity, we are really looking at the tiny capillary pores. That's something important to remember. And then, if you reduce water to cement ratio, you saw yourself what happens to porosity. It reduces too. So B is obviously wrong. And D, why D is wrong? The pores are always between 0.5 and 5 millimeters. No, they can be much smaller, much smaller. So that's also wrong. So the answer is really C. When you have higher porosity, you are less durable. And remember what durability is. Admixtures. So we have 2 minutes. So one thing that I actually wanted to ask you is that I don't go over describing the different admixtures, etc. in detail in the class. You can go through the notes and the book, because I like us to spend more time on concrete mix design in the class than the time we have together. So I guess you all agree with that. Because you can read about admixtures on your own in my point of view. There's no reason to listen to it. So I'll start with concrete mix design on Monday. However, you need to know about admixtures. And there is also some other information at the end of this lecture. I think this would be a better plan. Make sense? There is a quiz on Monday on the whole packet of cement.